Hello, for today's video we're talking about section 9.2 about series and convergence. So today we're basically going to define what an infinite series is and talk about what it means for it to converge. Next lesson we are going to talk about specific series, the geometric series, and then the nth term test for divergence of an infinite series. So what is an infinite series? Well, an infinite series is an infinite sum of a sequence. So some reminders here, this giant epsilon or capital epsilon is summation notation, and we start at the first term, so this tells us we're starting with n equals 1, and we're going to infinity, so those are our indices. So pay attention to that bottom index. That's really important because most of the time it'll be 1, sometimes it'll be 0 for specific series, and sometimes it may even be a different number. So just something to pay attention to make sure that you don't accidentally get a problem wrong because you didn't pay attention to that little tiny number. But like I said, most of the time it'll be what you think it should be. It should be 1 or 0 depending on the type of series, and we'll talk about that. So last lesson and before we've been talking about sequences. So what is a sequence versus a series? So a sequence is just a list of numbers. So a sequence might be a sub 1, a sub 2, a sub 3, so on and so forth. And perhaps it's 1/2, 1/4, 1/8, right? So on and so forth, 1 over 2 to the n, and it continues. And a series is going to be the sum of a sequence. So a series is when I add them together. And an infinite series then, of course, goes to infinity. And so an example might be 1/2 plus 1/4 plus 1/8 plus so on and so forth. And I continue to add that. So when we talk about the sum of a series, we like to look at the sequence of partial sums. So partial sums means I'm not adding all of the terms. I'm just going to add some of them. So if I look at the first term, and then I look at the sum of the first 2 terms, and then I look at the sum of the first 3 terms. And so how we signify this is capital S with the subscript telling us how many of the terms I have added. So S sub 5 would be the sum of the first 5 terms. And S sub n is going to be the sum of the first n terms. And so as I look at where this S sub n goes, the limit as n goes to infinity, that is going to be the sum of the entire series. So here's the definition of a convergent and divergent series. So if we look at our partial sum, S sub n, okay, so if I have that for my series, then I can say if the sequence of partial sums converges to S, then my series from 1 to infinity of a sub n converges. And if the limit S, and that limit is called the sum of the series. So remember that S is the limit as n goes to infinity of my partial sums, S sub n, okay? And so that's going to be what we're looking at. But if my limit of those partial sums doesn't exist, then I have a series that diverges. All right, so let's look at some examples. So our first example, we have 3 examples, and for each of these, we're asking, does the following series converge or diverge? So in order to do this, we're going to look at the partial sums. So if I have the series from 1 to infinity of 1 over 2 to the n, my first partial sum is going to be 1/2. My second partial sum, is going to be 1/2 plus 1/4, which is 3/4. My third partial sum is 1/2 plus 1/4 plus 1/8, which is 7/8. My fourth partial sum, 1/2 plus 1/4 plus 1/8 plus 1/16 is going to be 15/16. And I can continue until I find a pattern, but that's enough for me to see the pattern. So the pattern for this is going to be my denominator is 2 to the n, and my numerator is 1 less than that. So 2 to the n minus 1 over 2 to the n. And so then if I take the limit as n goes to infinity of S sub n, that's going to be the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n, which is just going to be 1. So then I can say that the series converges and its sum is 1. All right, so the series from 1 to infinity of 1 over 2 to the n converges to 1. All right, and here's kind of a visual for this specific series. So if I have 1 square unit, my first term is half of that, and then a fourth of that, and then an eighth of that, and a 16th of that. And essentially, I'm just going to keep going round and round and round, and you're going to end up with, basically, you're just taking up all of the space, right? So there's a visual of how that sum is going to be 1, because whatever space is left, I'm going to take half of it for the next term. All right, here's my next example. So my next example is the series from 1 to infinity of 1 over n minus 1 over n plus 1. And so if I write this out, we notice that my first term is 1 minus a half. My second term is a half minus a third, and then a third minus a fourth. And so when I put these all next to each other, I can see that part of each term will cancel out part of the other term. So let's go through our partial sums. So I have 1 minus a half. My second one is 1 minus a half plus a half minus a third, which is 1 minus a third. My third partial sum, 1 minus a half plus a half minus a third plus a third minus a fourth. So then I end up with 1 minus a fourth. And if I continue this, we're going to see that all of the terms within these terms are going to cancel except the 1 in the beginning and the last term of the term, right? The last term within the term. So here I get 1 minus a fifth because the fourths, the thirds, and the halves will cancel. So if I continue, my partial sum will be 1 minus 1 over, and then this will be n plus 1. So if I look at this, I want to take the limit as n goes to infinity of 1 minus 1 over n plus 1. And so then we have that this term right here is going to go to 0. So my sum is 1. So I would say that the series from n equals 1 to infinity of 1 over n minus 1 over n plus 1 converges to 1. All right, my last example is just the sum of the terms of 1. So this is going to be 1 plus 1 plus 1 plus 1 plus whatever. And so if I continue that, my partial sum will just be the number of terms I have, right? So if I have 2 terms, 1 plus 1 is 2. If I have 3 terms, 1 plus 1 plus 1 is 3. So my partial sum is just n. And the limit of that as n goes to infinity is infinity. So this one diverges. All right, so our second example here, where we have the things that cancel within the terms, that's what we like to call a telescoping series. So a telescoping series is of the form b sub 1 minus b sub 2 plus b sub 2 minus b sub 3. Let me put this down a little bit here so we can talk about the a terms. Okay, b sub 3, and then my third term would be b sub 3 minus b sub 4. And then my fourth term, b sub 4 minus b sub 5, so on and so forth. Okay, so this first term right here, that's a sub 1. This would be a sub 2. This would be a sub 3. This would be a sub 4. Okay? So when I look at this, my nth partial sum will always be the first term because there's nothing to cancel that. and then one more than n, because so if I sum the first four terms, 1, 2, 3, 4, the last b to sub 5 will be the thing that does not cancel, right? So the first one and the last one do not cancel. So my nth partial sum would be b sub 1 minus b sub n plus 1. All right. So if I want to think about what my sum is going to be of a telescoping series, well, this is going to actually exist and converge if my b sub n's approach a finite number. Okay, so my telescoping series converge if and only if the b sub n approaches a finite number as n goes to infinity. Okay, and so then my s would equal b sub 1 minus whatever that limit is as n goes to infinity of b sub n plus 1. All right, so let's do an example of this and kind of put some of this into practice. Okay, so I have the series from n equals 1 to infinity of 2 over 4n squared minus 1. And so we know that this is a telescoping series because it tells us that in the problem. So how we can put it in that form is partial fractions. Oh, so exciting. So for partial fractions, remember your first step is to go ahead and factor your denominator. So I get 2 over 2n minus 1 times 2n plus 1. Then your next step is to set that up where I have a over one of those factors, 2n minus 1, plus b over the second factor, 2n plus 1. I'm going to let you pause the video right now and try finding the values of a and b and confirm with me. So you should have found that a is 1 and b is negative 1. So we get 1 over 2n minus 1 minus 1 over 2n plus 1. So then I can see that this is the same thing. This series is the same thing as the series from n equals 1 to infinity of 1 over 2n minus 1 minus 1 over 2n plus 1. So what does that look like if I start writing out my terms? So if I start writing out my terms, I get 1 over 2n minus 1 minus 1 over 2n plus 1. So my first term is 1, so I plug in a 1 for n. And I'm going to get 1 minus, let's see here, if I plug in 1 over here, I get 2, 3. And then my next one is going to be a third minus a fifth. And then my next one is going to be a fifth minus a seventh, and so on and so forth. And so what I get here when I think about my s sub n, I am basically going to have the 1 minus, and then whatever is left. So that term right there is going to be this term right here, right? It's just the last term within my term, which is 1 over 2n plus 1. So then if I take the limit as n goes to infinity of that, I see that this last term here goes to 0, so my entire limit is 1. So then I can say that my series from n equals 1 to infinity of 2 over 4n squared minus 1 converges to 1. Okay, so that's a telescoping series. And that is all we have for the lesson today. Next time we're going to do